All right, everyone, let's lock in our learning objectives for this unit. We're focusing on two key skills today. First, you'll develop the ability to choose the right indicator for a specific titration. We'll get to the details of how to do that soon. Second, we're going to use these indicators as practical tools to figure out the pH of solutions when we don't know what they are. Indicators are essentially pH paper or solutions that change color at different pH levels, and they're incredibly useful in the lab. By the end of this section, you'll be confident selecting and applying them correctly. Now we're shifting to what success looks like for you in this unit. Your first criterion is that you'll be able to take an indicator chart, which shows you which colors correspond to which pH values, and use it along with data you're given to figure out the pH of an unknown substance. Think of an indicator chart like a decoder. You observe the color change when you add your indicator to a solution, match that color to the chart, and boom, you know the pH. This is the practical application of everything we've been discussing about how indicators work. Now let's dig deeper into what indicators actually are and how they work. Indicators are weak acids or bases themselves. This is the key. When they're in different forms, their acid form versus their base form, those two forms have completely different colors. That's why the same indicator shows different colors at different pH levels. And here's something important. Each indicator doesn't change color instantly across the entire pH scale. Instead, it has a specific transition range where it shifts color. Bromethymol blue, for example, only changes noticeably between pH 6.2 and 7.6. Outside that range, it stays the same color. This is why we pick different indicators for different pH ranges we're testing. Here's the complete indicator toolkit you need to know. Each indicator has its own specific pH window where it actually changes color. That's the transition range. For example, litmus works beautifully between pH 5 and 8, making it perfect for neutral solutions, but it's useless in highly acidic or basic environments. Notice how different indicators cover different pH zones. Phenolphthalein is your choice for detecting bases above pH 8, while methyl orange is ideal for weak acids around pH 3 to 4. This is why chemists choose specific indicators based on what pH they're trying to detect. You pick the indicator whose transition range matches your solution's expected pH. Now we're applying what you learned about indicator ranges to a practical scenario. I'm giving you 3 different pH values: acidic at 2, neutral at 5, and basic at 10, and you need to predict what color each indicator shows. Remember, methyl orange works best in acidic conditions around pH 3 to 4, while bromethymol blue operates in the neutral to slightly basic range. Think about whether each pH falls within or outside each indicator's transition zone to determine if you'd see a color change or just the default color. Now let's move beyond indicators to a more reliable tool, the pH meter. Instead of relying on color changes, a pH meter measures the actual electrical conductivity of a solution. It works by detecting the voltage difference between 2 electrodes placed in your sample. Since acids and bases conduct electricity differently based on their ion concentration, this voltage correlates directly to pH. The big advantage? You get a precise numerical reading, like 2.92 on the display, rather than guessing whether a color is more orange or yellow. This is why labs use pH meters for accurate work, while indicators are better for quick field tests. Now it's time to check your understanding with an exit ticket. 2 problems that pull together everything we've covered. First, you'll calculate pH from a known acid concentration, using the relationship between molarity and hydrogen ion concentration. Second, you'll work backwards. Given a pH value, you'll find both the hydronium and hydroxide concentrations using the inverse of the pH formula and the water ionization constant. These problems test whether you can confidently move between concentration values and pH scale positions.